Alright, morning. Let's start lecture, and so we'll get on to the topic of differential equation. Okay, so we're going to talk about first order differential equation first. So some of you are probably you learned a little bit differential equation first order in the first year, but we'll start from scratch. Okay? Yeah. So first of all, what is the general form of first order differential equation? Okay. So we in the last lecture we actually had a general format. Okay. So for this particular kind of things, we call that implicit. And for this kind of format, it's called explicit. Okay. Yeah. And in this course, we're going to consider mainly this explicit situation. Okay. So basically, we're going to consider, right? We're going to mainly linear ODE. So first of all, we'll consider this linear equation, which is a0 x y prime plus a1 x y equal to f of x. So this kind of formality here, okay? This kind of format. Now, for this kind of format here, okay? And I think I need to see just a few things. You know the way we write derivative, The way we write derivative, when we write y prime, we know this means taking derivative y, right? Yeah. But if we don't know what independent variable for the function y is, so we don't know what derivative y with respect to, basically, right? Yeah. So if you write dy over dx, you know exactly, y must be a function of x, so you're taking derivative y with respect to x, right? Yeah. So that's the difference here, right? This is basically sort of a general here, it's taking derivative y. The other notation, when you use a y dot, right? That's Newton's notation. This notation generally refers to the time derivative. Basically, this generally refers to dy over dt, right? Yeah, so those are just sort of things here. So differential equation, this x here is a dependent variable. So y is a function of x. Maybe use a t, maybe use something else, though, so that really depends on the question, all right? For this linear equation, I can simplify this a little bit. If I divide both sides by a0 x, I would get y prime plus a1 x plus a0 x y equal to this, right? Equal to this. Okay. Then, as you can see, the coefficients in front of the y, right? I can define it, okay, as another format. I'll call it this. Okay. So this is basically another way of writing this linear, right, ODE for the first order. Yeah. Yeah. So you have a p of x here, you have a q of x here, right? Yeah. And what we're going to assume is okay, this p of x and q of x, both of them are continuous. Okay. Okay. They're both continuous over a certain region that you're interested. Okay. So if we're trying to solve this differential equation from, let's say, for x from a to b or some kind of that region. So we're going to assume that two things are going to be continuous, okay, over that region. Okay, so this is basically the linear equation that we're dealing with here, right? Yeah. So they can be constant, okay? They can be constant, or they can be time. They can be a function, okay? Now the other thing is we're gonna learn in the next lecture. We're gonna call the so-called separable. Okay. We're gonna look at the separable equation. Okay. We're also gonna look at the separable equation. So the separable equation will be very similar like this one, but it will be slightly different format. Okay, just the way we call it separable equation because we are able to separate the equation to solve this differential equation. If you have time, we can look at another one called exact form. Okay, exact format. So it's sometimes called exact differential equation. Okay? And this format here is when we learn 248, we're going to actually look at it a certain time. Okay, so that's overall what we're going to look at it here. Okay, yeah. So first case, if I look at this differential equation, and the first case we're going to look at is when f of x equal to 0. So this time is 0 here, right? That's what we call it, homogeneous kind of situation, right? Yeah. So first thing is homogeneous. And homogeneous case is means y prime plus pxy equal to 0. Okay, so that's homogeneous case. Yeah, I found a Chinese software to record screen. So far so good, eh? It's not frozen. So we'll see how it goes. Yeah. So now how do we solve this one here? And this one here, you use a so-called separating variable technique. Okay. Separating variable technique. Yeah, so this is pretty easy. So this one, I think probably in your first year you probably learn a little bit of solving this one here, right? So how do we separating variable meaning you do this, okay? When you look at this equation in here, when you're given such kind of equation, number one thing you need to be sure is, okay, so this y got to be a function of x, right? You look at this one here, if this is a function of x, then y must be a function of x, okay? So then this means this y prime will simply means dy over dx at here, okay? Yeah. So then what I'm going to do is I'm going to just basically move this term at here, okay? Move this term over to the right side, okay? To the right side here. So that becomes dy over dx equal negative this, right? To this, okay? So separating variable, now this d at here, this d operator here is called differential, right? Differential. So that's not a partial. So basically you can treat dy or dx as a sort of a separate quantity. So you can manipulate. So it's like a quantity you can multiply, you can move, you can divide like that. All right? Yeah. So what we can do is we put this dx over to the right side and then move the y to the left side. Okay, move the y to the left side. And with that operation, we would get what? Dy over y here, and negative, and px dx here. Right? Px dx here. Okay? So, up to this stage, and this is good now, separating variable, right? Separating variable, meaning, see, we're putting all the y's together, and we're putting all the x things together, right? Yeah. So then you can integrate. Then you can integrate now, right? Yeah. So we integrate both sides. Okay. So all you need to do is just add an integration sign here. Okay, just add an integration sign. Okay, just like that. Okay, integrate. So this is a y function. So the integrating with respect to y, this is very simple. So this got to be what? Ln absolute y, right? Yeah, absolute y. And this side here, we're talking about general case, so we don't know what px is, so we'll just leave it. But if the question is given, you will know what the px is, so you'll be able to carry out this integral. Okay. Yeah. Okay. Now, technically speaking, we need to plus a constant c at here. Okay, yeah. Plus constant c.
Just on one side?
Yeah, one side is good enough. Yeah, because you can plus a c1 here, plus a c2 here, right? And then a c1 minus c2 is then a c, so we just call it c here, right? Yeah. Is that good? Yeah. Okay, so then further simplifying it, you take exponential of both sides. Okay, so basically you operate, okay, take an exponential of both sides here. So then this side will become absolute y, right? Absolute y. And the other side is e to the power of this thing here, right? To the power of this, okay? To the power of this. Okay. So e to the power of this, this is basically what e to the power of a plus b, right? This is the power a plus b. So which equals to e to the power of a, e to the power of b, right? A, b. And the b here is a c, so e to the power of c, that's another constant, isn't it, right? So we'll just call it another constant. Let's call it, maybe just call it a here, right? It's okay? Yeah. So basically the e to the power of c, we'll just call it constant c, constant a, okay? Or you call it c again, that's fine, okay? And then the other part is just this guy here, right? Yeah, just this, e to the power of a. So that's basically the solution of that homogeneous differential equation. But I guess you don't really like to have absolute sign at here, right? So if you get rid of the absolute sign, so that means the y will equal to positive negative a e to the power of px dx, right? That would be this case, okay? Yeah. So positive and negative a, so which means what? Which means the solution for the y here can be a positive value, can be a negative value, right? Yeah. So whether it's going to be a positive value or negative value, it's actually going to depend on the initial condition, right? So this guy here, so the value of this, okay, depends on initial value, or sometimes we call it initial condition, IV, initial, okay. Let's call it initial condition. Okay, initial condition. Okay, yeah. So in other words, I guess I don't really need to keep this positive and negative thing here. You know what I'm saying, right? So all I can do is I'll just let y equal to a. So this a is different from that a, okay? I mean, I'll use another. Let me use a b here. So this is going to equal to b of this, right? What's the b's value? B's value going to be determined by initial condition. Okay, that's basically how it's going to be. Is that good? Yeah. So this is a very simple case, homogeneous. Okay, just remember to separate the variable, and the rest of the work is just an integral, right? Yeah. Any questions? Yeah. All good? Yeah. So we can take a look at a very simple example. So y prime equal to negative 2xy, and x is from negative infinite to positive infinite. Okay. So when you look at, I guess right now it's simple, right? But as the number of type of the differential equations you learn, there are more types there. The first step is you need to identify what kind of differential equation you're dealing with, right? And then you apply appropriate technique for that type of differential equation. Okay. For this one here, it's just separating variables. So it's just going to be dy over y equal to negative 2x dx. Okay, yeah, 2x dx. So the other thing I noticed in the past is people trying to remember, okay, this is a type of formula, this is a type of differential equation, and then try to remember the final results of this differential equation, right? Yeah. So that could work, and but if you remember one thing wrong, forget a negative sign or something like that, right? And you will end up the whole thing as the wrong results. So what I would strongly recommend is don't try to remember what the final results is. Huh? Yeah. If you can remember 100%, great. But otherwise, it's easy. So just remember the way to solve this kind of differential equation. Okay, that's how it works. So ln y, okay, equal to integral, and which is x squared negative, right, plus constant c. Okay, constant c. So then y in the end will equal to a constant e to the power negative square. Okay, that's it. So if I graph this thing here, okay, if I graph this one here, so the y graph will totally depends on the a value at here. Okay, depends on a value. So when a value is positive, you have a graph looking like this actually. Okay, and when a value is a negative, you have a graph, okay, looking like this. Okay, so this is when a is greater than 0 and a is less than 0. Okay. Okay. Any questions? Yeah. Okay. Oh, good. Now we said about initial condition, right? We said initial condition. So basically, the question is, okay, how do I get the a value? And your initial condition problem. So initial condition problem, sometimes I also call it initial value problem. Okay. Yeah. Initial condition meaning the question, yeah, not just give you this differential equation. It also give you a condition saying, okay, y of a equal to b. Okay, this is an initial condition. Okay, or sometimes called initial value. Okay. So what does that mean? That means when in this case this is a independent variable of x, right? When x equal to a, the y value equal to b. So that's what it means. Okay. Now initial value or initial condition means the x, right? The x starts at where? The x start at a, right? So basically here x, okay, start at a, right? Start at a. Okay. Now if this is what it means, right? If this is what it means here, if I go back to my to this equation here, right? To this equation, okay. Now in this equation, you see this integral here, right? That's a indefinite integral, right? So you didn't specify the integral limits at here, okay? You didn't specify. The reason we didn't specify is because we don't know where x starts, right? Or the question didn't tell us where x starts. But now if the question tells you the initial condition, initial value, so now you know where the x starts. So if you know x starts, then instead of an indefinite integral, we can use a definite integral. So that y, you can write it as, what I use, b, right? B e to the power negative integral, right? So instead of using it, we integrate this starting from a here, okay? Starting from a here, right? So where do we end then, right? Where do we end then? Well, remember, where do you end? It didn't tell us where to end, right? And actually, in general, in this kind of differential, you don't have to know where it ends because you're trying to get general solutions. You know, after this initial condition, what will be the system response at a certain future time, right? So it's gonna be ending maybe anywhere along the x-axis. So what do? Basically, the upper limits will be just the x, okay? So the rest of the things you have to change that just slightly. Originally, the integral here is a p of x dx here, right? But now because your upper limit is x, in order to differentiate the dummy variable, and instead of using x, you will use maybe anything other than x. Okay, so use a u here. So this is essentially, if you have an initial condition, then that solution will basically become this. Okay, become this. Yeah. So you can actually think about this, right? What is the difference between what is the difference between this guy and this guy? What is the difference between this? Come again?
One has the additional problem.
Yeah, sure. But what will be the difference between the final results for these two? Okay, so this one has a constant here, right? This one has a constant. What about this one? So let's see this equal to f of x plus c. Okay, so f is antiderivative, right? It's antiderivative. So what about this guy here now? This will be what? F of x minus f of a, right? The fundamental theorem of calculus. So what would be the difference between these two? The difference, this is a constant here, this is a constant here. Well, as there is a constant, there is a difference because you don't know what this constant, you know what this constant, right? So the only difference between these two actually, it's a difference of a constant, right? So if you use this, subtract this one here, if the c is different from this, the only difference between this is the difference of constants, right? Yeah, okay? So basically here, just the difference of a constant, okay, of a constant. Okay. All right. So now let's look at, you know, I haven't finished. Let's look at the initial condition and this guy here, right? So what it says here is, I don't know what the b is yet, right? I'm trying to find a b value. Now let's apply initial condition. Okay, apply initial condition. This is the initial condition here. Apply initial condition means you let x equal to a. And let's see what happens, right? So let x equal to a. Letting x equal to a basically means this is your solution, then you are getting is y of a here, right? Y of a here. And b, I guess we're not going to touch it yet. And then this integral becomes a to where? It's x, you set it to a, right? You set it to a. And pu and du. Okay, set it to a. The integral, when the integral limits are the same, the integral itself becomes 0. So this e to the power 0 becomes 1, right? So this basically becomes b. Okay. At the same time, you have your initial condition. Initial condition tells you is y of a equal to b, right? Y of a equal to b. So which means this capital B just basically the same as your initial condition, the small b there, right? Small b. So then with this solution here, then my solution for the y is actually just basically b here negative a2x pu du, right? So that's the initial condition here. Okay, yeah. So the other way of getting this value of a capital B, okay, the other way is I'm going this way here. What I just did here is sort of giving you a general solution here, right? This is sort of like a formula. Okay, this is sort of like a formula here. Okay, it tells you this capital B is just the same as the initial condition. Okay, but in reality, the general way of solving this the initial condition problem is you can still go over the whole process like this and getting this guy, okay, getting this guy, and then substitute the initial value into here, solve for the b. Okay, yeah. So we'll see examples like this next. Okay, we'll see that next. Yeah. So let's take a look at this example here, right? See this example here. It's RC circuit. Okay, it's RC circuit. Now we're interested in the this is output of system. There's no input, right? There's no input here, but you can add an input here. Okay, once added input, it's not homogeneous anymore. But without input, you can derive using TCL law the differential equation governing this circuit is this guy here. Okay, so this is the differential equation governing this equation here. Okay, so Vc is a function of t, and this is a homogeneous at here, right? It's homogeneous. So we're trying to solve for the Vc here, and solve Vc. So you can go through this separating variable technique. It's very simple. And we'll be able to arrive at the Vc, okay, which is a function of t, and that equal to a constant a e to the power negative 1 over rc at t, right? Like this is a solution here. Okay, this solution. Okay, so once you get a solution then I will say, okay, I'm going to tell you what the initial condition is. So let's see initial condition Vc, right? Vc. Okay, starting from 0. So at t equal to 0, this voltage across the capacitor equal to a certain value V naught. Okay, certain value V naught. Okay. Yeah. So basically, this means at t equal to 0, right? At t equal to 0, the Vc equal to V naught. Okay, so then I'm going to try to get the value of A at here, right? Well, I guess I know what the A is going to be. The A is going to be just V naught, right? So, but let's verify that, right? So what we do is we let Vc equal to, let t equal to 0, right? Let t equal to 0. Letting t equal to 0, then the left side is basically V naught. And the other side is A e to the power 1 over Rc multiplied by 0. Okay? So overall, this is 1, so that means A equal to V naught, right? Equal to V naught. So this is another way basically getting the initial condition here, right? Yeah. Is that good? Yeah, so this RC circuit is very simple. I think you're probably doing some experiment in 255. This RC value at here is called what? So sometimes you can use a symbol tau equal to RC. This is called time constant. Okay, called time constant. Okay. Have you learned this? Not yet? Yeah? Yeah. Good. No? Okay. Anyway. Any questions? Okay, all good? Okay, so that's all about homogeneous first order differential equation, right? Homogeneous one. So now let's take a look at the second case, which is the general or nonlinear or non-homogeneous case. Okay, so non-homogeneous. Non-homogeneous, so we're dealing with is okay, this general format, right? General. So the Q of x is not going to be 0 anymore. Okay, it's not going to be 0 anymore. It's just this guy here. So let's see, how do we solve this one, right? How do we solve this one? Okay. Now, I think you're probably very tempted to do is this. See, previously what you did is you just put an integral on both sides of the equation, right? And then you might think, can we just do the similar thing? Can we just put another integral on both sides of the equation, right? Yeah. And we can try it. You know, if you do that, then what happens is, if you put an integral here, 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 right? And of course, you want a separate variable. Basically, this is dy over dx, right? So you move the dx over here, here, okay? However, you see the problem here is, so if I do that, I'll get something like this, right? Yeah, something like this. Yeah. But the problem, yeah, this is good. This is good. The problem is this guy here, right? The problem is this guy. I can't do the integral of this one because why? Because I don't know what a y is, right? We're trying to solve for the y, so we can't put anything in here. So basically, this one is a problem here. Or in other words, if you just simply use the separating variable, if you just do the integral, and it won't work, right? So what we call this is it's not integrable. Okay, so it's not integrable. And we have to figure out a way. So then the question is, we need to figure out some sort of a approach, to make it integrable. All right. So then we have this technique called integrating factor methods. Okay, integrating factor methods. So here's the logic here, okay? So let's go through let's get clear with how the logic works here. So we're trying to make it integrable. So what we do is, we introduce a function, introduce a function, sigma x, introduce a function. So you don't have to call it sigma, you can call it use any symbols you want, So I'm just using sigma here. So I'm going to introduce a function sigma x. Then I'm going to multiply this sigma x to both sides of this equation, to both sides of the equation. So then what I get is sigma x here, y prime here, sigma x px y equal to sigma x qx, right? Yeah. So we are not changing the original equation. We just multiply the original equation on both sides with sigma of x. Okay. Yeah. And the idea here is this, right? The idea is, remember, the objective is trying to have an integrable differential equation. So now, the whole left side here, is a mix of y and an x here, right? It's a mix of y and an x. So then, very ideally, you would think is, so is there some kind of a sigma x such that, okay, such that this whole left side okay, this is the whole left side, right? This is the whole left side. Such the whole left side can be written as this. Okay, can be written as this. Okay. So let's follow the logic here. Okay? You always start from the question, asking, is it possible? If it is possible, then what would be that, right? Yeah. So that's the thing here. Now you look at, you see this one plus this writing. This is y prime dy over dx. Okay. So why is this desirable, right? Why is it desirable? Because why? Because if I have this guy here and then this guy equal to this, I can simply apply what? The separating variable technique, right? Separating the variable technique. Okay. Yeah, so then my whole original differential equation will become integrable. Okay. So that's the thing here. Okay. So if this is possible, right? See the logic here. If possible, then right, original, okay, dE, right, becomes d over dx sigma y equal to this sigma x qx here, right, equal to this now. Yeah. Up to here, a little bit clear. Okay, let's finish this step here. Okay, yeah, just a second. Yeah, just a second. Yeah, let me see this one here, right? If possible, then the original becomes this. Now, why is this better? Why is this better? Why is this better than the original, this guy? Well, first of all, this guy you can integrate, right? But this guy, why is this better? I can move this dx to the other side, right? And then this just be basically this, right? And why is this better? Because now I can integrate, right? I can integrate. So then I can integrate. Right? Then I can integrate. Why can you integrate? Now, because you see the left side here, right? The integrator for d anything is what? Is that anything? Okay? So this side here just simply just sigma y here. Okay? Sigma y. And of course plus constant, but what just illustrates the idea here. And the other side depends on what the sigma f x is. You can, right, do a regular integrations. Right? You can do regular integrations. Okay? Is that good, right? Let me go back to the original here. Let's answer the question of Dustin's question here, right? Yeah. What's the logic behind doing this one here? The logic is behind doing this. You want to solve this question, this differential equation, and you want to solve that with the simpler approach. So you multiply each side by a function sigma of x. We call it integrating factor, and we ask the question is it possible we can find a sigma x function such that the whole left side can be written into this guy here, right? Can be written into this. If it's possible, then instead of solving the original one here, I'm solving this guy here, all right? Solving this one. Solving this one means I can simply separating variable, and I can obtain a format like this. then the y will be simply equal to 1 over sigma multiplied by this guy here, right? That's going to be the solution. You see, right? That's going to be the solution, and plus a constant c like that. Okay, that's going to be the solution here. So you narrow down yourself, okay, with the starting the logic here. So then you narrow down yourself to a question is the question here is that possible, right? Or can we find such kind of sigma x? Okay, that's basically the whole idea. Okay, yeah. Now, before we try to show you how to find the sigma x here, so let me give you a case if it's possible here. The thing is that okay? Yeah, yeah. So let's say y prime plus 1 over x, y equal to 4. Okay, equal to 4. So that's a non-homogeneous case. Okay, so the q of x equal to 4 here is constant. Okay, so what we're going to do is, so if what we're going to do is, I'm not sure what a sigma, I don't know what the general way of getting a sigma, but in this case I'll tell you what it is. I'll multiply sigma equal to x, okay, on both sides. Okay, I'll multiply this guy on both sides here. So if I multiply both sides here, let's see, what do I get? I get x dy over dx plus x multiplied by 1 over x is 1, right? So then multiply by 1, okay, like this. Okay, like this. So what is this equal to? Look at this one here. Look, this just equal to xy prime. Okay, this equals xy prime. Why is it equal to xy prime? You probably wonder, is it true? Well, if you don't trust me, what you can do is you can use what? The product rule of this derivative here, right? Use the product rule of this derivative. If you use the product rule here, so this xy prime, what does that equal to? That equal to what? X prime first, then y, right? So x prime is 1, so y. Then x, y prime, right? The second one here. That's product rule, right? That's product rule. That's basically what this is, right? That's what this is. Okay. So this simple case study here basically tells us is good. It is possible, right? It's possible. You can definitely find a sigma here, multiply both sides, and you can simplify the other side to this simple format, and then use a separating variable technique, right? So the question is possible. And the next question is, how do we find that? Use a general approach to find the sigma of x. So let's try to find the sigma of x here, okay? Sigma x here. Okay, so then let's go back to our assumption at here. This is our assumption here. Yeah. So starting with the assumption is there a sigma x such that this equal to this, right? Equal to this. So you're putting this into this format. And the right side here is d over dx sigma y. So let's start from the right side here, right? Start from the right side. Okay. Starting from right side basically meaning, let's look at what does this guy, okay, give us sigma y at here, okay, sigma y here. Okay, so maybe I'll write it down a few symbol here. Sigma is a function of x, and y is also a function of x, right? So just like the example here, what I did is I use a product rule trying to verify, right? So over here we try the same thing. Let's expand this one here, right? Expand it. Expand it using product rule, and that'll give us sigma y prime plus sigma prime y, right? Prime y. And if I write it using d, so that's sigma this, d sigma this, okay, like this, right? Yeah. So that's what this is. And everything starts from this question here, right? So whether this is possible equal to this. So then what we do is let's put it back here. Let's compare, right? Let's compare this one, right? This is what you want equal to. You want this one equal to what? Okay. this one here, okay, you want to it to be the same as which term? Same as the sigma x multiplied by dy over dx plus sigma x px and then y, right? And then y, right? So you want this to be the same as this. In other words, you want this guy to be the same as this, right? Because this is from product rule. Okay. So let's compare this term and this term here. Okay, let's compare these two here. So did you see anything that they're the same thing? Oh yeah, the first one is the same thing, right? So you want these two the same. The first one is already the same thing. So which means the second term here has to be the same as each other, right? So which means what? Which means the second term here has to be the same as, so d sigma over dxy has to be the same as this one. Okay, has to be the same as this one. And what's the similarity here? There's a y here, there's a y here, right? So the two y's gone. So that gives us that gives us this. So look at that. That's very good. Because why? Because everything, the y is gone, right? The y is gone. Because when y is around, that's causing problem. We don't know what the y is. We're trying to solve for the y. Now y is gone. We know p of x, and everything in terms of x. This is actually what kind of differential equation? This is actually the homogeneous, the first type, the homogeneous first differential equation, right? So then, what technique would you use to solve for? What technique would you use to solve for sigma? Separating variable, right? We just separating variable. So the d sigma over sigma equal to px dx. Okay, px dx. Is everybody following here? Yeah. So let me write down here. Let's get what sigma is. So what's the solution for the sigma? This is very much similar like the example there. So the sigma equal to what? E to the power px dx. Okay. So you might think is, oh, you probably should have a constant a somewhere here, right? Yeah. However, okay, remember what we're doing. We're trying to find a possible sigma of x, right? We're trying to find a possible sigma x. Basically means I don't need you to find me a general sigma of x. I only need you one. One is enough. So I can set this a to 1, right? You want to set it to 2? Fine, right? Yeah. But the 1 is enough. So basically, right up to here, you get a solution for the sigma. This sigma will be able to satisfy that whole assumptions. Okay, with this sigma here. So let me go over this thing here again. Okay, let me go over this logic here. So we started the question saying we wanted to find a sigma such that, okay, when we after multiplying the sigma to each side of the equation such that the whole left side, okay, can be written into here, right? Can be written into here. So the way the logic works is, you say, okay, I wanted A to be the same as B, right? Then if you want that, then you have to look at the B part. How do I make the B the same as A, essentially, right? So that's why we look at this quantity here. Look at this quantity. You want this one to be the same. Okay, then what's this B here, right? What is this B here? So that's why we do this step here. This B here is basically this quantity, right? Product rule. And what do you want? You want this guy to be this. They want this guy to be this. In other words, you want this guy to be the same as this, right? To be the same as this. Okay. So you want to find a sigma of x such that this is the same as this, and they happen just conveniently that the first term here is the same as this first term. So then the second term has to be the same as the second term right here. And there's a y for each on each side here, so you cancel the y, and you end up with just d sigma over dx of this. And then you can separate in variable, put all the x together, put all the sigma together. And now you can integrate, right? Then this is going to be a possible function sigma. Okay? It's going to be a possible function sigma. Is that good? Yeah. So once you have this sigma now, and you're pretty much you're done the job. You have solved the question, right? You have solved the question here, because what did I do at here? I did this whole portion based on what? Based on the assumption that I have a sigma, right? Based on the portion I have a sigma. If I have a sigma, my solution y is this. And now, what is the sigma? This guy. So all I need to do is what? Just substitute this one back to where? Back to here. Right? Back to here. So that'll be the solution for the y. Okay? Yeah. Yes?
With sigma of x and sigma of basically the same thing. If you have like sigma of x, then you just wrote sigma. Are those the same idea?
Come again? Sigma.
They have like sigma of function x, and you just wrote it as sigma.
Oh yeah, same thing. Yeah, if I don't have a sigma of x, or just a sigma, that means just sigma is a function of x.
Okay.
Yeah. Is that good? Yeah. So let's take a look at the example. We don't have time anymore. Eh? Yeah. Okay. So we'll take a look at example in the next week. Yeah. Yeah, just a second.